Okay, so example 3.
It doesn't even sound like it doesn't even spell like
Remember, you can use the calculator that's on the SEMATech website, but you need to load a ROM, and those ROM files are on my other maths page. If you remember, I showed you how to do that once. It works well in the Chrome browser. I got it to load. Okay, so right now the RAM is cleared. But we never go to the calculator until we already have something written down on our paper. Okay, it's just a number cruncher. It doesn't provide any thinking or insight. Well, it might provide some insight as a tool. So it says to find the values that are guaranteed by the mean value theorem. All right, so this is a polynomial. It is continuous everywhere, and it's differential everywhere, and we have a closed interval. So we're not going to say all that again. We're just going to go for it. So again, the first thing is f prime of x, the derivative, not always equals 0, right? If you have trouble remembering what to do, but always the difference quotient. So that's f of 2 minus f of negative 1 all over 2 minus negative 1, which is 2 plus 1. So that would still count as a difference quotient even though it's 2 plus 1, right? Because everybody knows that subtraction is just adding the opposite, even the people that grade your AP exams. Cool. And now we'll get a check for the setup then. So now we have to decide how much we want to do by hand and how much we don't want to do by hand. The derivative, I think I will do by hand, 3x squared plus 4x minus 1. But now f of 2, do I feel like plugging in a 2 to that gigantic equation? It's probably not going to be too bad, all right? But I just want to kind of show you the power of the calculator. If it's a calculator question, this might be kind of labor intensive to evaluate the numerator, okay? So what you can do is you could subtract it minus, and then f of 2 minus f of negative 1 all over 2 plus 1, or you can call that 3. And now it's equal to what if you bring it across? 0, yeah. So we essentially brought that entire quantity across, and now it's equal to 0. 0 is a great number when you're trying to solve an equation, okay, because you know where 0 is. It's also known as the x-axis. So here's what you could do to let the calculator do the rest of the number crunching for you. I'm going to turn mine on, power on, sweet. Go to y equals, and in y1, since we want to refer to f, type in your function, not your derivative, but your function, x cubed, 3x cubed, no, x cubed plus 2x squared, and then minus x. Okay, sweet. Now, go ahead and turn the graph off by going to the equal sign that's highlighted and hitting enter. It will now be unhighlighted, which I pulled it way too up. Yeah, you can't see. There we go. So it's in Y1, so we can still access it from any home screen, but it's not going to graph it because that's how we are going to solve equations. We're going to solve them graphically. Now in Y2, we're going to type in this left side right here. Okay, we're going to put that in Y2. So here we go, 3x squared plus 4x. That was a pretty easy derivative to get, minus 1. And now minus, we're going to go to the horizontal division bar, which I remember is what? Alpha y equals, and it's n over d. And now we're just going to let the calculator compute f of 2. So to do that, remember we hit alpha trace, and we put it in y1. So open parentheses of 2 minus, same thing, alpha trace y equals of open parentheses negative 1, close. Oops, I didn't put the 1. Like that. And on the bottom, let's say I'm not real sure with my addition skills, 2 plus 1. Or you can go for it and call it 3. It's up to you. Okay, now here's the thing that, and I think this is the first time we've done this year. Your calculator, your 84s, your 83 series, 84 series, they're all set up to find zeros for you. There's a command that allows you to find a 0, left bound, right bound. You have to scroll. But I find that it's just easier to find the point of intersection, which your calculator can also do. So I would always recommend, once you set it equal to 0, to actually, bless you, graph 0 in some other y. Okay, graph 0. So now I have a 0 sitting in y3. Okay, now comes the time to graph it, but because it's a mean value theorem or a Rolle's theorem or an IVT or an EVT, whatever the case may be, we're going to set our own window, okay? Go to your window, and I get negative 10 to 10. Is that good, or do you want to change it? Negative 1 to 2. You're not going to be tempted by outside values that may live outside the interval. There may be some, but you're not tempted by them because you don't even see it, right? Don't even buy the chocolate cake. Now, here's the good part. We're trying to find the x-intercept on that interval. Y min negative 10, Y max positive 10. That's good. That's symmetrical, so it keeps your x-axis right in the middle. But in the case that the graph may be designed to like hug the x-axis a little bit and make it kind of unclear, does it cross? Does it bounce? Just stretch that out to begin with. I always go negative 3 to 3. Okay? It keeps the x-axis in the middle, but you're stretching it vertically a little bit. So you could tell right away. Now hit graph, and we're looking for x-intercepts. There's guaranteed to be at least one. Guaranteed to be at least one. But there may be others, and the suspense is just awesome. Right? Like, what other types of programming is Disney Plus going to add? Are they going to put some of their famous ABC series on there because Disney owns ABC? Right? Or is it just going to be the Star Wars Mandalorian as the... Hey, wait, it's still graphing. There might be another one. Come on. Hey, it's done. You see it's done in the top right? So now here's how we find it. You ready? Second trace is your calculate menu. Number 2 is 0. Your calculator can do that. But you're going to have to like scroll to the left and scroll to the right. We're going to use number 5 instead, intersect. Okay? Now look how easy it is. If there's only 2 graphs and there's only 1 point of intersection, all you got to do is find your enter button and click your heels 3 times like Dorothy. Enter. Second curve, it should throw you on it automatically. Enter. And then for your guess, because there's only 1 point of intersection, enter. Right? That's a lot easier than scroll, enter, scroll, enter. And it's working. There it is. Okay. And so now on our iPad, we put x equals 0 point. And how many decimals are we supposed to report? 3. So 7, 8, 6. If you put more than 3, some people say, can we put more than 3? Yes, you can, as long as they're correct. You can't put, it's correct to 3 decimals, and then I'm going to add like some 7s. And I'm a big fan of making 4s like that. Right? So that's no longer correct. So if you're going to put more than 3, make sure they're correct, but you can round or truncate. In this case, rounding or truncating, it's the same number. Your calculator should give you the correct answer to 3 decimals, okay, based on its whatever, however it does it, stores it. I don't know, ask Skylar Vestal last year. All right, now here's the thing. If we needed to use that number for something else, which very often we will, let's go to the home screen, second mode, get out of there. If you hit X, enter, it stores it as X. Okay. Now, for what it's worth, if you hit alpha 1, it also stores the Y value in case you ever need the Y value and it's an ugly decimal, it temporarily stores them in X and Y. But as soon as you go back to the graphing screen and do something else, it'll override X and Y with the new values. So if you're going to find more than one, always store it as something else. So you can hit X stow. Stow is on the bottom left, right above on. And I like choosing A. It's right there. It's the first letter in the alphabet. It's right below the alpha button, so you don't have to travel too far. And then you hit enter, and boom. Okay. And if you store it as A on your calculator, you want to come back over to your iPad or whatever you're working on your paper and call it A over there. Now make sure there's not like a sharing violation, like you're finding, bless you, the area of an object, and you're using A for the area of something, because now, you know, we're confused on what A is. So choose a unique variable, all right? And that's it. There you go. That's not too bad, right? Y'all can do that. But notice it all started with us setting it up on our paper/iPad first, all right? Now, just for kicks and grins and giggles and whatever, let's go back to y equals, and let's get rid of that other function, the 0, okay? We'll delete it. Now if I hit graph, it'll graph it again. By the way, if you preferred, you could graph the f prime and y 2 and then the difference quotient in y3 and find where they intersect. The only problem is they may intersect somewhere off your screen, right? The y values could be anything where they intersect. And so you're going to have to go search for them now. But if you set it equal to 0, I think we all always know where 0 is, yes? 0 is always on the x-axis. So as a problem-solving tool, that's kind of what I would recommend. All right, so let's find it now. We should get the same answer. Now we go second trace number. Now I got to use 2. And look, I can't just hit enter, 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 because now it's going to ask me a lower bound. So as you come in from the left, the lower bound is going to be below. I'm going to click enter because I get a visual. And now I have to click to the right. Look at all this scrolling. Look at all these extra steps I have to take. Literally steps to get across the x-axis. Now I've crossed the x-axis. I have a nice visual. I'm going to hit enter. And you notice your calculator puts little arrows at the top, or if you have a fancy one, it'll put vertical lines. And you're basically saying, calculator, I think it crosses the x-axis in that interval. I don't know why they still have guess on there, because it doesn't really help. It doesn't speed it up or anything. So you can always use your right endpoint as your guess, and it'll find the answer. It says 0 now. There it is. So I don't care which method you use. I think it's just easier to graph 0 and go enter, 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 right? Boom, 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 3 clicks, done. Now, if it intersected more than once, then you'd have to scroll to the one you want, or if there's more than 3 curves, you can either turn one of them off and only graph 2, or you could, bless you, when it says first curve, second curve, if you vertically toggle with the directional pad, you could pick the equations that you want. All right, sweet. Go ahead and do example 4 on your own. Guided practice, and now you have individual practice. This one is a non-calculator question. Example 4, non-calculator. Yeah, yeah. As you work down, it's good to kind of like keep 2 separate sides and simplify the difference quotient all the way to a single number, so you can see what the average rate of change is, or the slope of the secant line. And then you can set out to solve. I even took the time to write out the word differentiable. Whew. Did you? You can always use MVT. That's an appropriate abbreviation. Mean value theorem applies because, so notice I answered the question first instead of doing F is continuous on the closed and differential on the open. Therefore, F or MVT applies. You can answer it flip. So again, that first line, F prime of X equals the difference quotient in terms of F, that's what I would highly recommend. If you deviate from that script, good luck in getting all the checks, even though you may end up with the right answer. Okay. So on this one, we end up with 2 answers, right? And we know we're guaranteed to have one, but sometimes we can have more than one. So at this point, if we walked away, the bottom line is always considered to be your final answer, by the way. Would we get credit? Or if this were a multiple choice question, should we take the answer that has both of them there? No. Okay. Which one do we toss out? 0. And it seems kind of, he's like, oh man, but he's right there. He's a left endpoint. Okay. Well, that's what makes the mean value theorem a little bit different than the other 2 VT theorems, because the extreme value theorem says that the global max and global min can occur on the interior or at a what? Endpoint, right? At an endpoint. But the mean value theorem's always discussing the guaranteed on the interior. Okay, where does it happen between the endpoints? Okay, so you can go ahead and well, let's keep going. I was thinking worksheet time, but we got 11 minutes. We could finish this today. If we can get to calculus cops today, that would be awesome. Okay, let's see if we get to calculus cops. All right, very quickly here. Let's just say if the mean value theorem applies to these functions on the intervals. This is example 5, because this could be a question in and of itself. We're looking at this function f on the closed interval from -3 to 5. Does the MVT apply? Yes or no? No. I mean, if you look at that right there, what does this function have at x equals 1? A vertical asymptote, right? Because you plug it in, you get 6 over 0. Non-zero over 0 is infinity. That means there's a vertical asymptote causing the y values to do that. It wouldn't be a problem on certain intervals, right? But it looks like 1, where the vertical asymptote is in the interior of our interval. So you could say no, because f is not continuous at x equals 1, and then here's what I would recommend adding. And why is 1 relevant? Because that is epsilon, the closed interval. Epsilon, right? That means is an element of or is inside that interval. So you're really hitting the nail squarely on the head. You're leaving nothing to doubt. 1 is relevant because blah, blah, blah. Now, if we're looking on the interval from like 5 to 10, there's still a vertical asymptote at 1, but mean value theorem applies because it's not on the interval, okay? All right, so the derivative would not be existent there either, right? It's not differentiable there as well. So either one. This one here, x to the 2/3 on the interval from -3 to 3. What alert are we on? Cusp alert, cusp alert, cusp alert. We have a fractional exponent less than 1. You know then at the root of the base, there's going to be a vertical tangent line. It could be a cusp that goes vertical and comes out like that, or it could be one that just goes smoothly through it. But in any case, it's not differentiable at what? What's the x value where the cusp is? Nope, it's at x equals 0, right? That's the root of the base. If the base again were like x plus 5 to the 2/3, now there would be a cusp at what? X equals -5, so on and so forth. The root is the value that you plug into the base that gives you a 0. So at x equals 0, is it continuous there? Yeah, it is, but it's not differentiable. So no comma g is not differentiable at x equals 0, which is on the what interval? If you put the closed interval, it's not wrong, but you want to put the open interval because you're talking about a differentiability argument, not a continuity argument. Otherwise, you could say it's not differentiable at x equals 0. because x equals 0 is in the interval from negative infinity to infinity. Oh, it sure is, my friend. But that doesn't mean anything here. Now, let's say you didn't want to be on cusp alert, right? You're like, okay, this thing is continuous. This is the same as the cube root of x squared. It's continuous everywhere. If you're not sure if it's differentiable somewhere, what could you do? Take the derivative and look at its domain. That's 2/3 times x to the negative 1/3. That's the same now as 2 over 3 cube root of x. And now you can see that x can't be 0. It's in the domain of the function, which means it's continuous there, but it's not in the domain of the derivative, so it's not differentiable there. And when you plug a 0 into g prime, you get 2 over 0, which is some type of infinity. So you know there's a vertical tangent line there. The graph of the derivative would have a vertical asymptote there because the derivative itself, the slope, is vertical. Okay? So cusp alert, cusp alert, cusp alert. Oh, we have 7 minutes. I think that's enough time for the calculus cops, okay? This is a nice application of the mean value theorem. The calculus cops have set up their elaborate speed trap on a busy, stretchy stretch of road. The road itself is stretchy. A suspected pumpkin farmer, they're not even sure if he really farms pumpkins, who uses the road daily to haul pumpkins to market, is suspected of chronic speeding well beyond the posted limit of 55. The calculus cops aim to finally ticket this unlawful transporter of seasonal gourds. How do they do it? Well, they set up 5 miles apart from each other, furtively, secretly parked behind a piece of scenery so as not to be seen. Calculus cop A spots the farmer with his jalopy loaded down with would-be jack-o'-lanterns. As the farmer passes cop A, he's clocked at a paltry 50 miles an hour, 5 miles per hour under the speed limit. That's what the radar gun said. Cop A, this is creepy. Cop A could have sworn that the farmer waved at him as he drove by, as if he knew he were there. Cop A immediately radios calculus cop B 5 miles down the road, whereby cop A starts his timer. Exactly 4 minutes later, cop B clocks the farmer cruising by at exactly the speed limit of 55 miles per hour. This time he clearly sees the farmer wave at him with a giant grin that would make a jack-o'-lantern jealous. After a quick calculation on his field issue TI 88.5, you only get those at the Calculus Cop Academy or eBay, he pulls out with his lights on to issue a speeding ticket to the ornery pumpkin farmer. Now here's the question. For what speed can they ticket him, and would it hold up in a court of law? Why or why not? Yeah, it would hold up in a court of law. Okay, so why is this a mean value theorem? Well, the mean value theorem, if we look at his position down the road, okay, here's his position in miles down the road in minutes, right? Is his position function continuous? Is it 5 minutes later? Yeah, it has to be, okay? Because for his position function not to be continuous, he would have to teleport, okay? Teleport. So unless the farmer can prove in court that he can teleport, we've got the continuity down. Okay, so what about differentiability? Is it possible for him to have a vertical tangent line, whether it's cuspy or not? No, because the slopes of this graph represent the farmer's what? Velocities. And if we have a vertical tangent line, his velocity is what? Infinity. Can the farmer drive infinitely miles per hour? I don't think so, right? So therefore, his position function is continuous on the closed interval from 0 to 5 minutes, and it is differentiable on the open interval from 0 to 5 minutes, right? Because he can't teleport or drive infinitely miles per hour. Therefore, by the mean value theorem, there had to be a time where his instantaneous rate of change of position, known as his instantaneous what? Rate of change, or his velocity, at some moment had to equal his average rate of change of position, which is his average velocity. We know how to find average velocity, right? Average velocity, let me write that first. Average velocity. Let me move it over here. All right, so all we have to do is compute his average velocity. Well, average velocity is displacement over time, elapsed time. He traveled what? 5 miles? Is that what it said? I get my numbers confused. 5 miles in 4 minutes? Yeah, I put 5 there. This is 4. He traveled 5 miles in 4 minutes. Now, that's his displacement, 5 miles. He could have gone like back and forth, back and forth, back and forth. He could have stopped and set up a pumpkin stand for a little while and not sold any pumpkins and kept going. But his displacement was 5 miles in 4 minutes. Well, minutes is not the proper unit of time we want. 4 minutes is 1/15 of an hour. Stay, change, flip. The TI 88.5 does this for you. You get 5 times 15 miles per hour, which of course is what? 75 miles per hour. By the mean value theorem, there had to be at least one time, even though we don't have it on the radar gun, where he's driving 75 miles per hour. And so we could ticket him for 20 miles over the speed limit, even though it's never shown on the radar gun. And will it hold up on court of law? Absolutely. Absolutely. Because it's called the mean value what? Theorem. Okay, now he's going to have to pay the fine. You probably shut down his whatever business he's doing, his racket. But as he goes out the courtroom, he does have the last laugh because for his average to be 75 when you caught him going 50 and 55, he had to be going what? Faster than 75. Once on the way up, he hit it. Once on the way down, but we don't know how much faster than 75 he was going. There's no way to tell. Okay. So that's a nice application of the mean value theorem. All right, no homework online tonight. No homework online tonight, unless your name is Rolly or Makeda.